Okay, a very warm welcome everyone. So we are starting our today's session on variational autoencoders. In the previous session, we have covered various concepts on autoencoders. Since we have started this series, we have explored a lot of concepts starting from the perceptrons, the sigmoid functions. Then we move towards reconstruction of images using recurrent Boltzmann machines, restricted Boltzmann machines, followed by we have implemented the concepts of autoencoding in order to reconstruct the images using autoencoders. Then we have improved the accuracy with multiple types of autoencoders. We have also used applications of deep learning in image denoising. And finally, in the previous session, we have started with the concept of variational autoencoders. So when it comes to variational autoencoders, you all have a quick idea that using variational autoencoders, we can generate variations of images given some certain number of images. So in our today's session, we will be taking up the MNIST dataset for using it as the image, and then we will be generating variation of images using that MNIST dataset. The concept which we will be implementing is influenced from this article. This article was published on 1 May 2014, which states autoencoding variational Bayes. So here you all can quickly understand the mathematics behind variational autoencoders. So I have got a couple of resources which we will be using in order to understand how variational autoencoders work. So just to have a quick understanding that what do we exactly what we want to do using this concepts of variational autoencoder, we would like to generate some images out of the data. Earlier, we have been introduced with the concepts where we have been either recognizing the images or we were reconstructing the images. But now we have to make use of neural networks in order to generate new images. And for certain examples we have taken in the previous session where I have shown you certain websites like the people does not exist, this person does not exist.com, which was a very nice example of generating adversarial networks where some random images have been generated by the machine learning algorithms. So what we will be doing is we will be making use of these articles and we will be generating something like this. So now our objective is to generate images somewhat like that. So initially we will be starting with the MNIST dataset, which is going to provide us the numbers. Now what we have to do is consider these two columns. What we are going to have, we are going to have certain numbers and we will be varying these numbers into variation formats. Okay, so suppose given a number 6 or given certain number, we will be having variations in two directions. The first variation will be the variations of parameter for the sample models 1, and the second variation will be on the second dimension. Okay, you can consider it as variations towards z2. So now what we will be having is, given an image, you can see that that image can be represented with different number of forms and another numbers can also be generated. So here, given this image 6, you all can quickly see out of the given image of 6, various other images of 6 of different types, as well as images of 0, and finally the image of 2 has been generated. So somewhat like this, you all can see here at the bottom, using the image 7, as soon as the variations have been applied, the 7 with different forms have been defined here. And finally, we have got 1 generated out of that image also. Okay. So depending on the parameters which we will be learning, depending on those parameters and depending on the given image, we will be generating new images out of the dataset. That's what is required. Similarly, in case if you want to see a real-time example of what variational autoencoders could be, this is a better example, and this is the image which I wanted to show you in the previous session. So you can consider one variation is on the y-axis and second variation is on the one variation is on the y-axis and second variation is on the x-axis. So now you can consider this. There are two types of variations happening. The variation which is happening on this y-axis is the variation in smile. Okay, you can quickly consider it as variation of smile. You can consider it as smile as one of the features identified from the photograph. Okay, so consider Z1 as an attribute or as a feature which has been learned from an image, and smile is represented on the y-axis here. So you can see that as soon as you see from top to bottom, the smile of this person is changing. Okay, along with that, in case if you want to see another variation, consider the variation as Z2, and I'm going to say that, let's say this is going to be the variation Z2. And second variation, second feature which we have learned here is the head pose. Okay, so you can see that the head pose of this person is turning. So from the left face, he is changing his face towards the right side. So now you can see that if we consider this variation, this is the variation number 2. So suppose given an image, what variational autoencoder can do, given some certain number of images, using those number of images, what neural network can do? Neural network can learn different number of features. Okay. Suppose our given neural network has learned 2 features, consider smile and the head pose. Now using these 2 features, what we can do is we can generate more number of images which are not available in the data set. So this could be an example of variational autoencoders. So what a variational autoencoder is? Variational autoencoder is a neural network wherein we have an encoder network and a decoder network. Given an image to the encoder network, we are going to learn some attributes. Now, depending on these attributes, we have to generate, we have to decode images in such a way that these decoded images these decoded images are the variational images. Okay, so till now you all have understood the concepts of autoencoders, wherein you can see, let's say we have an image X. Consider you had an image X, and that image X multiplied with your consider X into Z plus bias, Z bias. Okay, or else we can say, let's not say it Z, let's say it as a kernel or weights. Okay, so suppose you have an image, so you have performed this maths over an input image and you have generated a hidden layer. Okay, so what a hidden layer generally was in an autoencoder network, that hidden layer was known as a feature which has been identified. Now using done was okay. So let me introduce a couple of more information here. Let's say we are going to make use of an encoder. Okay, using that encoder, the hidden layer has been generated, and using that hidden layer feature, we have been using a decoder network. And what the decoder network was doing, it was reconstructing the image earlier, reconstructing the image. So what you were able to achieve was you were able to achieve the appropriate X which was given. Now, what we want is, once we will be using variational autoencoders, we actually want that the images should be generated in a format like this: X1, X2, X3. Different number of images should be generated. Okay, I hope this is clear to everyone. So, how will we be able to perform this operation? How can we generate variational images using the variational autoencoder? So that is what is the objective. Okay, so whatever statement I have given here, this statement is actually a reference to this data set which you all can observe here. So multiple number of faces has been generated by identifying 2 features: the head pose features and the smile features. Okay, so let us just quickly get started with understanding the concept. So what you guys need to do is, let me just quickly save this image as well for future reference. Now, how you are going to design a variational autoencoder network. So in order to design a variational autoencoder network, we have an image over here, and I'm sharing that image with on chat with all of you. You all can use this image later. So here is an image which I have identified, which could explain the concept of variational autoencoder in a nice way. So consider you have some input features, some this is your input layer where you would be having some n number of neurons. Now over this input layer, one of the biggest concept or one of the most important thing which we have to understand here, how we are going to perform variations in it. Okay. So because earlier what we have been doing is we have got the original image and we had a predicted image, and out of identifying the loss between the predicted and actual image, we have been adjusting the weights and we have been identifying that the generated image is an actual image generated. Now, how we are going to generate variations? That is a big question. So, in order to generate variations, we have to have a network wherein we can introduce variations in some way, and we should be able to control the network in such a way that the generated images are relevant to the input data set available. So suppose I have given a data set of numbers from 1 to 9, and suppose using that 1 to 9, my neural network is generating some unnecessary image which is not a number. So that is of no use, which means that neural network will become uncontrollable for us. So what we have to think of is, we have to think of the concept where we have to implement a neural network which is a controllable neural network, and we have to introduce the variations in such a way so that the images generated are the images which are relevant to the inputs available. Okay, so that is what we have to identify. So in order to identify that, there is a nice article which is available, which we will be discussing, which is going to discuss the mathematics behind the variational autoencoder network. But before that, I would like to give you a quick idea about how practically you will be implementing and what all things you need to focus on. So first of all, what do we need is, we need to introduce some information where you're going to have these two things. Let me just quickly draw here. So first, what you have is, you have the mean information available. Okay, let's call it as mean. And second, we have available is the divergence. Okay, you can also call it as the standard deviation. Standard deviation. Okay, we can also call it as covariance. Okay, and later you all will be calling it as divergence as well. Okay, so earlier what we used to do, we had our input images and we apply some weights as a dot product to the inputs, and then we added the bias, and using that we used to calculate the hidden layer. But now what we have to do is, we need, instead of generating a hidden layer, we actually have to generate or construct a Gaussian distribution. That is what is the objective. Okay, so in a variational autoencoder, we will be having an encoder network. This encoder network will have some input number of neurons, which would be available over here. Let me just define it as input images. So these input images will be applied with two metrics, and you can consider these metrics as the mean metrics and the standard deviation. And using this mean and standard deviation, we are going to generate a Gaussian distribution. Okay, so you will be generating a Gaussian distribution. So what could be the Gaussian distribution we are going to? So you can consider this Gaussian distribution as a conditional distribution in probability, which is actually known as the probability of occurrences of event with some relationship to one or more events. Okay, so here there are two things which you need to focus on. We can quickly consider this as conditional and prior we will be using. So we will, I'll cover that in the equations part when we will proceed to the next tab here. So using this constructed divergence, what is your objective in this case? Your objective is to generate a sample. Okay, and this sample will be generally known as Z, and this is known as a latent variable. Okay, in autoencoder, there is a very important term, and this term is known as the latent variable. Okay, so you guys does not need to be confused with what latent variable is. Latent variable is just a hidden layer which learns a feature. Okay, So latent variable is nothing but a feature of an image which has been learned by your neural network. But this feature has been learned not directly with the weights, but in fact it has been learned with a constructed Gaussian distribution. Okay, so that's what we need to understand. So now using this, we have to pass it through the decoder network. Now we will be having a decoder network. This decoder network will be applied with rectified linear units. Okay, so using rectified linear units, finally you are going to generate some sample number of output images by applying sigmoid over it. Okay, you will be applying sigmoid over this layer, and finally you're going to get variational images generated. I hope the objective is clear to you. So there are a couple of new things which have been introduced. The first thing which has been introduced in an autoencoder, in a variational autoencoder network, is the encoder itself. Okay. Now, what do we generally, with respect to the reference paper, when you will be reading that research paper, you will understand that variation of images can be generated from the decoder itself. Okay, you just need this part in order to generate variations in the images. Okay, but in order to have the controlled output, generally what happens is, if you will be using only decoder to generate the variation images, this will be uncontrollable. Okay, and it is also known as intractable most of the time. Intractable. So this is uncontrollable. So to make it controllable, N has been introduced, and the encoder has got certain new features in it, and these features are identified as introduction of mean. Sorry. Okay, introduction of mean, along with introduction of standard deviation and a constructed Gaussian distribution to generate your latent variable z. So this is something very important which you will be introducing in your code today. Previously, you all have implemented the concepts of implementation of dense layers and the input layers. So you can generate an input layer. Then using that input layer, you have been earlier generating the dense layers. And after that, after the dense layers, you have been generating the images. But now you you have to introduce this constructed Gaussian distribution within your encoders. So that will give you a variational autoencoder. Now, once you have got to see about this, let us just quickly understand the mathematics behind it. Okay, so kindly keep a copy of this image in your mind, so that once you will be understanding the technical understanding of this, which means once you will be reading the mathematical equations behind it, you have to remember this figure in your mind. Okay. Now, I think I have already shared a video also with you, which I guess has explained quite well about what a variational autoencoder is. And please confirm me on chat how many of you have viewed that video which I've shared. The video from Stanford University to understand variational autoencoder. Just confirm me on chat. Okay, only one. Okay, no problem if it's not clear. It will be clear today. Okay, so let's just understand the concept behind it, behind the video. So the video is based on this article, not exactly this one, but let's start with this one. I'm going to give you a quick idea. So what exactly is required in order to get the variations in the images. In order to get the variations in the images, you need a network like this, wherein you need to know the feature, and using the feature, you have to give that feature to deconvolutional layers, which means you will be reconstructing the images, and finally you're going to get an image somewhat like that. Okay, let's say a variational image. That is what is the objective of variational autoencoders. Okay, now if you want to see a common definition here, I think they don't have a definition over here, but let's skip that. So now what we have to do is, when we have to generate the variations among the images, you need to have some latent vectors and variables, and this feature is very important. You can consider this as the important vector or a variable which is required, and we generally call this latent variable as Z in this case. Okay, so your latent variables are known as Z, and Z plays a very important role in generation of variational images. So consider the fact that you have an image X. Okay, you have an image, and that image is known as X, and this image may have a number of features. Okay, so a number of features, like it would have colors. Okay, for example, let me just show you what all we can see about this cat. We can see the colors, we can see the texture of this cat image. Along with that, we can see the eyes and physical attributes. Okay, we can see the nose of the cat, we can see the tongue of the cat, we can see the teeth of the cat. So consider these are some n number of features. Okay, now using this image, your neural network is going to learn some of the features. You can call these features as variables also. Okay, so let's call this variable as Z, and you can also call it as a latent variable. Another name you can give to this variable as a latent variable, and consider any latent variable. So suppose I will be taking one latent variable as, let's say, eyes, let's say. Okay, so, or you can take the mouth, extra, anything, colors and eyes, anything you can take. Okay, now using these latent variables, you can generate variational images. Okay, you can generate variational images, but the problem, generally the most important problem here is the control over the network. Okay, so in case if we don't have the control over the network, we won't be able to achieve the appropriate outcome or the accurate outcome of the variational images generated. Okay, so we are working towards that problem, that how we can generate a network which is a variational autoencoder network, which is a controlled auto encoding network. Given the features, some latent variables can be generated in such a way that these latent variables are controlled latent variables, and then using a decoder network, some variations of the images can be generated. This is the objective of this variational autoencoders. Okay, is the objective clear to all of you? Please confirm me on chat अगर आप लोगों को ये objective बिल्कुल clear हो गया है. सिंपल सी बात है, वेरिएशनल ऑटो एनकोडर में क्या है हमारे पास, हमें एक इमेज के थ्रू वेरिएशंस ऑफ इमेजेस जनरेट करने हैं. जैसे ही हमें वो इमेज मिलती है, हम उस इमेज के अंदर से फीचर्स को लर्न करते हैं. उसमें से आप फीचर्स को लेटेंट वेरिएबल भी कह सकते हैं. लेटेंट वेरिएबल वो वेरिएबल है जो कि वेरिएशन इंट्रोड्यूस करने में आपको हेल्प करेगा. सो आपके न्यूरल नेटवर्क के अंदर वो ऐसा वेरिएबल जिसके थ्रू आपकी इमेजेस में वेरिएशंस होंगे, वो वेरिएबल लेटेंट वेरिएबल है. ठीक है, अब ये लेटेंट वेरिएबल अचीव करने के लिए आपको एक एनकोडर चाहिए. तो वो एनकोडर हम कैसे इंट्रोड्यूस करेंगे? अभी तक जो हमारे एनकोडर्स थे उसमें हम इनपुट लेयर्स को लेते थे और उनके साथ में हम वेट्स को मल्टीप्लाई करते थे और बायस अटैच करते. बट अगर हम अभी कोई भी रैंडम वेट्स अलॉट करेंगे तो हो सकता है कि वो फीचर्स चेंज हो जाएं. ठीक है, तो हमें कंट्रोल्ड फीचर्स जनरेट करने हैं. अभी तक जो हम फीचर्स जनरेट करते थे वो फीचर्स कंट्रोल्ड नहीं थे, बट अगर हमें कोई कंट्रोल्ड फीचर जनरेट करना है ताकि हम उस कंट्रोल्ड फीचर को यूज़ करके वेरिएशंस इंट्रोड्यूस कर सकें इमेज के अंदर, वही हमारे वेरिएशनल ऑटो एनकोडर का काम है. ये बात क्लियर है आप सभी को? अगर क्लियर है तो कंफर्म कीजिए मुझे, सो दैट हम आगे बढ़ें।
Sir, latent vector helps in differentiating different features.
Yeah, latent vector is just a variable, and just a variable which has been learned from the feature. बट आगे वेरिएशंस इंट्रोड्यूस करने के लिए बहुत सारे और भी अभी इक्वेशंस आएंगी साथ में, जो भी मैथमेटिकल फॉर्मूले हैं, बट वो अप्लाई होंगी इसी वेरिएबल के ऊपर। ओके, so variable, latent variable is a normal variable which will be used for generating variations of images. but वो variations होंगे कैसे, उसके लिए mathematical equations अभी आगे हम देखते हैं कि कौन सी equations हैं जिसके थ्रू variations generate हो। ओके, is that clear? Am I audible? Okay, so now let's see. So अब क्या होगा, अब आपको इस तरीके से एक नेटवर्क बनाना है, ठीक है? तो अब आपका नेटवर्क कैसा बनेगा? ये नेटवर्क कुछ इस तरीके से होगा। ये आपका एक वेरिएशनल ऑटो एनकोडर नेटवर्क है। यू कैन कंसीडर इट एज अ वेरिएशनल ऑटो एनकोडर नेटवर्क, ठीक है? वेरिएशनल ऑटो एनकोडर नेटवर्क की खास बात ये है कि एक सैंपल इमेजेस को यूज करके आप मल्टीपल डेटा जनरेट कर सकते हैं, और उस मल्टीपल डेटा जनरेट करने का बेनिफिट ये है कि आप जो भी क्लासिफिकेशंस या प्रेडिक्शंस करते हैं, वो प्रेडिक्शंस आपकी इम्प्रूव हो सकती हैं, ठीक है? बाय डिफ़ॉल्ट क्या होता है न्यूरल नेटवर्क्स में, आपने एक इमेज दिया, उस इमेज के थ्रू आपने अपने नेटवर्क को ट्रेन कर लिया, तो अब आपका नेटवर्क उस सेम टाइप की इमेज को ही आइडेंटिफाई कर सकता है। बट अगर उस इमेज के अंदर हम थोड़ा सा भी वेरिएशन कर देते हैं तो वो प्रेडिक्शन करने में हमारा न्यूरल नेटवर्क फेल हो जाता है। तो इस प्रॉब्लम्स को ओवरकम करने के लिए हमारे पास वेरिएशनल ऑटो एनकोडर्स होते हैं, जो कि क्या करते हैं कि आप एक सैम्पल इमेज दोगे, उस या एक सैम्पल मतलब कुछ सैम्पल इमेजेस आप दोगे, उन सैम्पल इमेजेस के बेसिस के ऊपर मल्टीपल वेरिएशंस ऑफ इमेजेस जनरेट की जाएंगी, और उन वेरिएशंस के थ्रू मॉडल को ट्रेन करके एक क्लासिफिकेशन या प्रेडिक्शन मॉडल बनाया जाएगा, ताकि अगर आप कोई इनपुट वेरिएबल प्रेडिक्शन के समय पे ले रहे हैं या कोई इनपुट इमेज आप प्रेडिक्शन के टाइम पे ले रहे हो, तो अगर उसमें कुछ वेरिएशंस भी हैं तो भी आपका मशीन लर्निंग मॉडल या आर्टिफिशियल इंटेलिजेंस मॉडल उसको प्रेडिक्ट कर पाएगा, ठीक है? ये बात आप लोगों को क्लियर है? अब होता क्या है कि ये काम करने के लिए हमें क्या करना होता है, सबसे इम्पॉर्टेंट चीज़ है, हमें सैम्पल्स जनरेट करने होते हैं, ठीक है? वी हैव टू जनरेट द सैम्पल्स, ओके? ये जो सैम्पल्स हैं ये हैं आपके सैम्पल्ड लेटेंट वेरिएबल, यानी जो फीचर्स हमने आइडेंटिफाई किए हैं उसके सैम्पल्स। तो हमें अभी जब हम अपना न्यूरल नेटवर्क बनाएंगे, वहाँ पे हमें एक सैम्पलिंग मेथड डिफाइन करना पड़ेगा कि हम सैम्पलिंग कैसे करते हैं। सैम्पलिंग करने के लिए आपको कुछ रिक्वायरमेंट्स हैं। क्या क्या रिक्वायरमेंट्स हैं? दो रिक्वायरमेंट्स हैं मेजर। जो भी आपके पास इनपुट इमेज होगी उसका आप मीन वेक्टर जनरेट करोगे और उसका स्टैंडर्ड डिविएशन वेक्टर जनरेट करोगे, और उन दोनों वेक्टर्स को यूज करके आपको ये सैम्पलिंग जनरेट करनी है, ये सैम्पल लेटेंट वेक्टर्स जनरेट करने हैं, ठीक है? समझ रहे हैं आप लोग? तो आप लोगों के पास एक एनकोडर नेटवर्क होगा। उस एनकोडर नेटवर्क में अलग क्या होगा? उस एनकोडर नेटवर्क के अंदर ये चीज़ अलग होगी कि आप अब उन फीचर्स को लर्न करने के साथ साथ आप उनको पहले उनका मीन जनरेट कर रहे हैं, उनका डिविएशंस जनरेट कर रहे हैं, उसमें से सैंपल्स निकाल रहे हैं, और फिर उन सैंपल्स को यूज करके आप उसे डिकोडिंग करेंगे। ओके, इज दैट क्लियर? So that's what we will be doing in. Now, how will that work and what all do we need to calculate in order to create a variational autoencoder network? So ये काम करने के लिए हमें क्या करना पड़ेगा? यहाँ पे कुछ मैथमेटिकल इंफॉर्मेशन अवेलेबल है आप लोगों के पास। सबसे पहली चीज़ तो हमें क्या करना होगा, हम जनरेटेड इमेज और रियल इमेज का मीन कैलकुलेट करेंगे, जिसके थ्रू हमें जनरेशन लॉस मिलेगा। ओके। उसके बाद में जो हमारा लेटेंट वेरिएबल जनरेट होगा, उस लेटेंट वेरिएबल का और गॉसियन जो हम कैलकुलेट करेंगे उसके थ्रू हम एक डाइवर्जेंस कैलकुलेट करेंगे, जिसको हम केएल डाइवर्जेंस कह सकते हैं या आप स्टैंडर्ड डिविएशन कह सकते हैं। तो एक तो आपके पास जनरेशन लॉस होगा, एक आपके पास लेटेंट लॉस होगा, और इन दोनों लॉस को जोड़ करके आपका ओवरऑल लॉस आइडेंटिफाई होगा आपके इमेज का। ठीक है, ये चीज़, ये इक्वेशंस इंपॉर्टेंट हैं, ये अभी हमें कोड में इम्प्लीमेंट करनी है। ठीक है, सो हाउ एंड वाई वी आर यूजिंग दिस, सो उसका जो डेफिनेशन है वो यहाँ लिखा हुआ है, we let the network decide this itself. And what do we let him decide? We let him decide. There is a trade-off between how accurate our network can be and how close its latent variables can match the unit Gaussian distribution. So latent variable और Gaussian distribution की matching के लिए हमने एक automatic equations define किए हैं जो automatically calculate हो जाएं, और उसके लिए हम क्या कर रहे हैं, हम loss calculate करते हैं। तो लॉस कैलकुलेट करने के लिए पहले दो सेपरेट लॉसेस कैलकुलेट किए जाते हैं। जो पहला लॉस है वो जनरेटिव लॉस है, कि जब आप कोई इमेज जनरेट करते हैं तब क्या लॉस होगा, वो लॉस मीन स्क्वायर्ड एरर्स के थ्रू कैलकुलेट किया जाता है। सिमिलरली रिकंस्ट्रक्टेड इमेजेस का लॉस है जो कि लेटेंट लॉस कहा जाता है। एंड ये लेटेंट लॉस को कैलकुलेट करने के लिए हम केएल डाइवर्जेंस का यूज करते हैं ओवर द लेटेंट वेरिएबल्स एंड द गॉसियन। ओके, सो फाइनल आपको एक लॉस जनरेट होगा। आप इस आर्टिकल को बाद में गो थ्रू कर सकते हैं सो दैट आपको अप्रोप्रिएट आइडिया लग जाए। अब ये हमारे लिए इंपॉर्टेंट है। ठीक है, ये हमारे लिए एक्चुअली सैम्पलिंग जनरेट करने में हमारी हेल्प करेगा। ठीक है, तो सैम्पलिंग जनरेट करने के लिए सबसे पहले हमें क्या चाहिए, सबसे पहले हमें चाहिए कि हमारा जो लेटेंट लॉस है वो कितना है। तो लेटेंट लॉस हम कैसे कैलकुलेट करेंगे, वी विल बी कैलकुलेटिंग दैट यूजिंग the mean value of the feature as well as the standard deviation of the vectors generated by our encoder network. So इसके लिए एक सिंपल सी इक्वेशन है, 0.5 into reduce the sum of mean as well as the standard deviation minus take a log of square of standard deviation minus 1। ठीक है, तो ये आपका लेटेंस लॉस का इक्वेशन है। ये कैसे कैलकुलेट हुई है ये इक्वेशन, इसको आप केएल डाइवर्जेंस के जो रेफरेंस आर्टिकल मैंने दिया उसमें आप पढ़ सकते हैं। ठीक है, सिमिलरली हमारे सैंपल्स जनरेट होंगे यहाँ पे। अब हमारे सैंपल्स जनरेट होने के लिए क्या होगा, हमारे पास कुछ इनपुट सैंपल्स हैं, बट उन सैंपल्स के साथ हम स्टैंडर्ड डिविएशन का प्रोडक्ट लेंगे और मीन को हम ऐड करेंगे। ठीक है, उसके थ्रू हमारे सैंपल्स जनरेट होंगे। बाय डिफॉल्ट पहले क्या होता था, हमारे पास हम वेट लेते थे, वेट इनटू इमेजेस, and this could be considered as the bias। okay, but अब ये वाली चीज चेंज होके हमारा कौन सा फॉर्मूला हो गया है, नाउ वी आर यूजिंग द फॉर्मूला लाइक दिस टू जनरेट द सैंपल्स। पहले हम जो सैंपल्स जनरेट करते थे, अब वो सैम्पलिंग टेक्निक यहाँ पे यूज नहीं होगी, बिकॉज इसके ऊपर हम कंट्रोल नहीं कर सकते हैं। ठीक है, वेट्स इनटू इमेजेस प्लस बायस को हम यहाँ पे कंट्रोल नहीं कर सकते हैं कि हमारे वेट्स कौन से हैं। इसीलिए हमें करना क्या पड़ा, वेरिएशनल ऑटो एनकोडर का कॉन्सेप्ट सिमिलर ही है सैंपल जनरेशन का, बट जो हमने वेट्स और बायस लिया है उसके लिए हमने स्टैंडर्ड डिविएशन और मीन का यूज किया है। इज दैट क्लियर? And this will help you generate the samples. So in addition to allowing us to generate random latent variables, this constraint also improves the generalization of our network. Okay, तो इसके थ्रू आप क्या कर सकते हैं, जनरलाइजेशन मीन्स आप कोई भी सैम्पल इमेजेस यूज कर सकते हैं और सेम इस मॉडल को आप मल्टीपल टाइप की इमेजेस के साथ यूज कर सकते हैं। ज़रूरी नहीं है कि सिर्फ आपको MNIST का ही डेटा सेट यूज करना है, आप कोई भी n नंबर ऑफ सैम्पल्स जैसे कि फेस एक्सप्रेशन, फेस सैम्पल Am I audible? Okay, so at last, till where have you all heard? I think you all are clear with generation of this samples, right? I think I got disconnected, so I'm just asking again. You all are clear till here how we are generating the samples? Please confirm me on chat in case if you all have heard till here. Okay, fine. Now what we are going to do, so once we are done with this, let's just go to the mathematics behind it. So I've shared a video with all of you in the previous session, and now what you all have to do, you have to make use of that video, and the explanation to that video is here. Okay, about variational autoencoders. This article has been posted by Jesse Sai maybe. So she has explained it pretty well what exactly autoencoders are here. So autoencoders you already know. I'm just going to give you a quick description of what this article says and the important equations behind variational autoencoders. So an autoencoder is something like an encoder function f of x, where x is an image, and any function, the function which we are using actually is an encoding function, and that encoding function for encoders was take an image with the dot product of weights plus the bias. That is your function for encoding. That maps some input representations x to a hidden latent representation of Z. Similarly, we have a decoder network that reconstructs the hidden layer Z to get back the input. Okay, so decoding, you already understand how we perform the decode, how we perform the reconstruction. So we have already done that with restricted Boltzmann machines. Okay. Now, what do we have to do is, now we have to focus towards the variational autoencoder mathematical equations here. So now what variational autoencoder mathematical equations suggest, so it says, as in regular autoencoders, we have encoder and decoder networks, but because we are modeling probabilistic generation, okay, this is the objective in variational encoder. Modeling probabilistic generation. This means we are going to generate probable images for the input images. So for this, what we are going to do, we generate a vector of means and covariance that represents Z. So instead of weights and bias, we use mean and standard covariance. Okay. So I'll just write here, instead of weights and bias as used as used in regular autoencoders coders, we use mean and standard deviation. You can understand standard deviation. You can also call it as covariance. Okay, in VAE, in variational autoencoders. Okay, I hope this is clear. Now, to generate this data, we want to sample from a prior over P of Z. Okay, so what could be considered as prior over P of Z? So prior is nothing but it can be considered as an uncertain quantity that would express one's belief before some evidence is taken into account. Okay, so you can consider it as a perception value. So this perception value is considered as P of Z. So P of Z is nothing but probability of calculation of latent variable Z. Okay, then using that probability, we generate our data X by sampling our conditional distribution. So there are two important concepts here. One is the prior distribution. Prior distribution, I have already told you, prior distribution is nothing but it is just you can consider it as a perception about something like, okay, that might be certain number of values, but we can actually implement conditional prior in statistics. The official definition of prior is that it is an uncertain quantity that we would express our belief before some evidence is taken into account. So evidence as in we are not sure that what it is going to predict, but some randomized variables, some randomized values we will be taking in. Similarly, conditional distribution, what it could be, conditional distribution is nothing but it is the probability of occurrence of the event with some relationship to one or more events. Okay, so if you have to understand about probability P of x given the z. Okay, so this means if you have some z variables available, so prediction of x or calculating the probability of x in relationship with z is known as conditional probability. Okay, so this is also very important for you all to understand via our decoder network. So using the decoder network, you have to perform the following. You're going to have the P of Z, that is the prior distribution, as well as prior distribution as in whatever is given to you, whatever latent variable you have achieved. Now using that latent variable, you are going to perform conditional distribution. That means you will be calculating or reconstructing an X, reconstructing an image using that Z. Okay, is that clear? So you can consider this prior as the latent variable which has been generated from the network, and using this latent variable you can perform decoding on it. Okay, you can perform a decoding, you can perform a decoder, and you can perform the decoder by generating x using z. Okay, so decoding x using z will be known as conditional distribution. Now, what we want to do is we want to estimate the true parameters of model theta. So theta is nothing but you can consider them as weights. Okay. So here we have to learn the weights, the appropriate weights, which are generally known as the true parameters of the model. Okay. Now, our prior should be a simple unit Gaussian. One conditional distribution can be represented this with a neural network. This is the decoder network, and we can try to train using a multi-level perceptron. So यहाँ पे आपके पास एक decoder network है. This is the equation of the decoder network which is given to you. So within this decoder network, first we have P of Z. ये जो P of Z है ये आपका latent representation है, ठीक है, जो prior है, prior over latent distribution, followed by हमारे पास P of X है using Z, and P of X using Z is nothing but your conditional distribution. Okay, so this is your conditional distribution, this is your prior. Okay, so ये दोनों values तो ठीक हैं, these two values are fine. Okay, once you will go through with the video, you will understand that both of these values are appropriately, but this decoder network will not work due to the integral symbol over here. Okay, so due to this integral symbol, our decoder network becomes uncontrollable. And due to this attitude of uncontrollable nature of this network, we cannot use this network for decoding of variational images. Okay, so post this, there was another model which was identified, but that also was intractable, and that model is this. Okay, so in this model, even in this decoder network, if you see, it has P x of z, this value is fine, that can be done. We have got some prior values of z, that is also fine, but these values cannot be calculated. Okay, probability of x cannot be calculated. Hence, again, this becomes a bad model, and this also becomes an intractable model. So we cannot perform this. We cannot calculate the value P of z with respect to given x. Okay. So now what is the problem and what should be the solution? The problem is that the given decoder models are non-controllable. So how can we make them controllable? So in order to make them controllable, which means how we can calculate the maximum likelihood that the variational images are appropriate images which are generated. So for that, the researchers have identified that variational encoder can be successfully built if we can add an encoder network to this decoder network. Okay. Earlier, what they have been thinking only of a decoder network while generating for variations of images. They were only thinking for a decoder network. But the solution has been identified as that if we can add an encoder network to the current execution network, which can allow us to derive a lower bound. Okay, this encoder network models our posterior probability. So this will be able to calculate our P of Z with X. So if we can successfully achieve the value of P of Z using X, then we will be able to generate the variations of images. So that means we do need to have an encoder network. And once this encoder network has been introduced along with a decoder, that complete neural network becomes the variational autoencoder. Okay. So now what we are going to do, so once we are done with this, so here they have derived the equation. So in order to understand about the derived equation, I would recommend you all to quickly go through with the video, with the logical video which I have already shared with you. Okay. So here the reconstruction of the data is also being done. Along with, we have also achieved the maximum approximate posterior distribution close to the prior that can also be calculated. So here we do have the formula, and I think this is the appropriate formula which we can make use of. So autoencoder is actually represented with this specific equation. Okay. So expectations of reconstruction of the image along with maximizing or making the approximate posterior distribution close to the prior values which have been generated. Okay. So you will get to have the appropriate explanation of all these things, how these have been achieved. So you can, I recommend you to watch the video so that you will be able to understand this mathematics behind it. In case if somehow if you are unable to understand that from that Stanford video, I'll give you an explanation in the next session. But that is very easy. So I recommend you to watch it and make some efforts in order to understand this mathematics behind it. So the final thing which we guys got to know is this equation. Expectation of log P of X given Z minus KL divergence of Q of Z using X along with P of Z. Okay. So this equation gives you two important parts. The first part, this is the first part, the log of P of X, and this part is generally known as reconstruction using the input data, reconstruct input data. And the second part is on the right side, and that is approximate posterior distribution near to the close to the prior P of Z. So prior is, I have already told you, it's that quantity which is the perception quantity. Okay. So both of these equations will actually help you achieve this. This is the approximate posterior distribution close to the prior. So using this, we can actually construct an appropriate variational autoencoder. So once we are done with that, let us just quickly understand now what we will be doing. So here is the reparameterization technique which will be implemented, for which I have already shared the paper with you, this archive.org, and you can understand about the implementations of the equation. Okay, so I hope they have specified all these algorithms here properly. Along with that, they have some variational approximation section 3 for the phase data. I think they have some references here also for the data sets which have been used for faces and for text and for speech. You can actually refer here, but these codes are in MATLAB. So I'll just quickly see if the equation, if any more theoretical information is available over here. Otherwise, we'll get started with coding our variational autoencoder. But majorly, I hope you all are clear that what all we have to do. The solution is introduction of an encoder. So we will be introducing this part where we will be generating the Gaussian distribution to generate the sample, and this Gaussian distribution will be actually calculated along with the mean and the standard deviation. So using that, we are going to generate the Gaussian distribution, and from that we are going to generate a P of Z. Okay, that is going to be the sample. And then using this sample, we will be generating our variational images. So using the sample, we'll generate a layer. Using the rectified linear unit, we'll be generating the another layer. And finally, with the sigmoid activations, we will be generating our actual output images. Okay, so let us just write here variational images output that will be generated. So that's what we will be doing here. Okay. Now, so, and one more thing, how to calculate the samples. I've already told you about calculation of the samples and the actual implementations which we will be doing in. So is the concept clear that what all you're going to do? You will be implementing variational autoencoder. And in case if you want to understand the mathematics behind it, here is the paper which actually explains everything, why it becomes uncontrollable. Okay. So the part which I have told you that this is going to be intractable and this cannot be evaluated. So why it cannot be evaluated? What could be the true posterior density? You can understand all of these things here. Along with that, the variational bound information is also calculated here, along with how that KL divergence will be calculated. So the KL divergence formula has already been given to you. So here is the KL divergence formula, which has been identified here. Using the KL divergence of latent variable and unit Gaussian, you're going to generate the latent loss. And from the generation and the latent loss, you're going to actually calculate the loss. And then using that latent loss, we will be implementing various stuff in order to generate the vectors using our encoder network. And finally, using the samples, we will be giving it to the decoder networks in order to generate the images. So there are some number of algorithms which have been introduced here, that what is KL divergence and what is the reparameterization trick and how we can back propagate in the network, along with the variational autoencoder example. So it's a very nice article which you all should go through. Definitely you all should go through, so that you will be able to understand the technical part as well. Now let's just quickly get started with designing of the autoencoders. So I'll quickly go to our previous script, autoencoder part 2, and within that we will be starting designing our variational autoencoder. Okay, so are you all set? Let's get started with designing a variational autoencoder. Okay, so I hope you all are understanding why do we need variational autoencoders. Variational autoencoders की हमें ज़रूरत इसलिए होती है क्योंकि अगर हमारे पास कुछ सैम्पल्स हैं और वो सैम्पल्स लिमिटेड हैं, तो हम उन लिमिटेड सैम्पल्स को यूज़ करके एक अच्छा प्रेडिक्शन मॉडल रियल टाइम डेटा के लिए बनाना बहुत मुश्किल हो जाता है. तो अगर हमारे पास वेरिएशनल ऑटो एनकोडर जैसी टेक्निक होगी, तो अगर हमारे पास सैम्पल्स कम भी हैं किसी इमेजेस के, तो उन सैम्पल से हम कंट्रोल्ड वेरिएशंस बना सकते हैं, और उन कंट्रोल्ड वेरिएशंस को बनाने के साथ साथ हम अपनी रिकॉग्निशन कैपेबिलिटी को इम्प्रूव कर सकते हैं ऑन अ रियल टाइम सिस्टम. ओके, सो जैसे मान लीजिए एक एग्जांपल लेते हैं, जैसे नंबर प्लेट्स हैं आज की डेट में. ठीक है, अब नंबर प्लेट्स अलग अलग फॉर्मेट की हो सकती हैं. ठीक है, तो आप लोगों ने देखा होगा कि मतलब दिल्ली में व्हेन वी ट्रेवल फ्रॉम वन प्लेस टू अदर प्लेस, आजकल कैमराज एक्टिव हैं ऑन वेरियस रोड्स. ठीक है, तो होता क्या है, ऑटोमेटिक चलान्स आते हैं आपके घर पे, तो इमेज रिकॉग्निशन तो होता ही है. अलॉन्ग विद आप देख सकते हैं कि ये बहुत हैवी एक्यूरेसी होती है कि अगर आप ओवर स्पीड हैं और रात में 1, 2, 3, 4 बजे भी अगर आप निकल रहे हैं और उतना लाइट इंटेंसिटी नहीं है उस एरिया में, स्टिल the images and the number plate are captured appropriately. So how they do that with such great accuracy? So they have got these numbers 1 to 9 and the numbers A to Z, and then they have performed a lot of variations on those characters, and using those variations the models have been trained in such a way कि in case अगर आपने different hand styles या different font styles के भी अगर नंबर्स हैं, तो तो भी वो ऑटोमेटिकली रिकॉग्नाइज हो जाते हैं. ओके, सो इट्स नॉट लाइक कि हमें हर तरीके की फॉन्ट के थ्रू हमें न्यूरल नेटवर्क को ट्रेन करना पड़ा, ऐसा बिल्कुल भी नहीं है. बस मोस्टली क्या करना पड़ा कि एक सेट ऑफ जो स्टैंडर्ड नंबर्स हैं उनके थ्रू ट्रेन किया मॉडल को, उनके थ्रू नए वेरिएशंस बनाए, उन वेरिएशंस के थ्रू प्रेडिक्शंस जब होते हैं तो यू कैन प्रिडिक्ट अ वाइड वैरायटी ऑफ प्रेडिक्शन इनपुट्स जो भी मिलते हैं, जो भी टेस्ट केसेस मिलते हैं. So that's why variational autoencoders are very, very important. Moreover, it is not limited to recognition of images. When you can generate data with artificial intelligence, then there are a lot of good things which you can do. So as you all can see uh, in the previous examples where we have seen that images or drawings or art has been created by artificial intelligence and the value of those arts are like lakhs of dollars. So all these things can be generated and we can use artificial intelligence where we cannot limit the case with default conditions. In case if the conditions are variable, then on those variable conditions also we can apply our variational models, and our variational autoencoders and generative adversarial networks could be capable of generating new information and acting accordingly with respect to whatever cases are encountered. So now let's get started with coding it. So how you are going to perform designing a variational autoencoder? We are going to implement similarly the way we have started earlier. We are going to make use of the layers like input and dense. We are going to make use of model, the MNIST, the binary cross entropy. We will be using all of these things. Then we will be generating our training and testing data set for MNIST. Along with that, we are going to define our neural network parameters. Then we are going to build our encoders and decoder model. And post that, once we are done with defining our encoder and decoder model, now we will be introducing the reparameterization trick. Okay. So what is the reparameterization trick which we will be exploring? This reparameterizing trick. So what is the benefit of reparameterization trick? So reparameterization trick is a solution to the problem, and the problem is that if we want to back propagate through our network in order to compute all the partial derivatives, back propagation cannot be flew through a random node. So by default, z value which has been generated, or the latent variable z, is a random variable. We are not sure that it is a fixed variable in your hidden neural network. Okay, so it's very difficult to regenerate back to the variations. So now, in order to overcome this solution, in order to fix this, a new technique has been introduced, and this is known as the reparameterization form, where this latent variable is defined as a deterministic node, and some new random nodes have been generated, and that was the deviations and the summation part. Okay, so instead of sampling directly from the random variable z, instead of generating from here, our reparameterization techniques, what they are doing is they are generating the node using the mean and the divergence. Okay, so this actually helps in overcoming the problem of back propagation. Okay, so this problem is actually solved by implementation of this concept. Okay, so once we are done with that, our z becomes a deterministic node, and using that we can go from x to the final output, as well as we can back propagate the network in order to learn the other partial derivatives and the other partial features, and then we can generate variations of images. Okay, I hope this is clear. So you will be implementing this part as well in the code. And once you are done with that, we have defined the reparameterization trick. So along with that, we will be calculating our latent variables using the samples generated. Then we are going to initialize our encoder and decoder models. And finally, we are going to plot the results. So that's what we will be implementing in. So that is going to be the overall implementation which we'll be taking up. So let's just go here to designing our variational autoencoder and let's get started. So here, let's just get started with importing the layers. So I've already told you, we import Keras layers and we are going to import the input, we are going to import the dense, and you will be using a function known as Lambda function also. Okay, so this time introduce Lambda as well from Keras layers. Similarly, you will be importing the models from keras.models. You have to import the model. Okay. Once you guys are done with importing the model, then what next you will be doing? We will be working out on the MNIS. I'm sorry. We'll be working out on the MNIST data set here. So let's just import the data set. We'll be using data sets and we're going to import the MNIST. Okay. So we have got the MNIST data set, as well as I have told you here in this article, we are using two important information: the mean value and the binary cross entropy we would be taking in. So for calculation of the generation loss, we will be using some of these features. So for them to calculate these, we will be using some loss functions from the loss libraries. So let's make use of keras.losses, and we are going to import mean squared error. Along with that, we will be importing binary cross entropy. Okay. So we will be using that binary cross entropy. Along with that, you are going to have the utilities, and from the utility, we are going to plot the variational autoencoder models this time. So for that, we do have a function known as plot model in the utilities of Keras. So let's just use from keras.util, we have to import plot model. Okay, plot underscore model. This is what we will be using. Okay, so as well as let's just import the Keras backend as well. From Keras, import backend as K. Okay. Now, along with that, we need a couple of more libraries. Let's import NumPy. NumPy we will be using for various functions. We will be plotting our graphs, which we will be generating for variational autoencoder. So for that, we will be using matplot live.pyplot as PLT, as well as we'll be using others. We don't need anything. In case if we need it, we are going to import that later. Okay, keras.utils. Okay, so these are some of the libraries which we will be requiring to designing the variational autoencoders. Now what next? So let's just process the MNIST data set. Okay. So in order to quickly read the data set, we are going to make use of NIST and we're going to call the function load data. Along with that, we are going to have your X training and Y training here. So let's just put that X underscore train. Okay. We will be taking this time the X and Y set for training, as well as the X and Y test for testing as well. You can use the similar way of representations which we took in the previous sessions also, but you can take X and Y both. Okay. Now, so once we're done with that, let's just, you can check the shape, the size of the image. So as we already know, the size of the images are 28 cross 28 pixels. Okay. So we are going to take the original dimensions here and we will be representing those original dimensions. We are going to convert them between the numbers so that we can represent it in the matrix, and we are going to generate training and test. Okay. So since we have to represent that on input layers as neurons between 0 to 1, so we'll be dividing that with 2, 5, 5 and so on. Okay. So let's do that. So we have got this. Let's take the shape X training dot shape of the number of columns we have, and we're going to define that we're going to have a 28 cross 28 pixels. So I have just directly defined it as an image because you can make use of this variational autoencoder with other different image sets also. So that's why we are coding in such a way that we will be automatically reading the columns, and whatever the image size is, irrespective of the MNIST data set, whatever the image size would be, our data will automatically be arranged so that we can make use of this variational autoencoder with other images also. Okay. Now, second, in order to grab the original dimension, since we already know that's a squared image, so image size into image size. Okay, this is going to be the original dimension of the MNIST image, which we have. Let's save that into an original dimension. So since we had the 28 cross 28 pixels, since we have 28 cross 28 pixels, okay, so we have got the original dimension of the image. Now what you can do is you can perform the reshaping and then you can convert that into training and testing. So let's use the reshape function. Using the reshape, we're going to provide the training information. Along with that, now what we're going to do, we're going to take it from -1 to the original dimension. Okay, so we are taking that order in such a way that we will be reshaping it to the information available in that complete training data. And after reshaping, we will be saving that into X training. Similarly, we will be reshaping the Y as well, the testing data for X test. So let's use it. X underscore test is equal to np dot reshape. We're going to take X test and we're going to take it from -1 to the original dimension. Okay. Now, so once we got the shape as well as once we have got the training and testing information, let's just convert that into float 32 so that it can be represented in the metrics. So we have got the X training. Let's change it to as type float 32. Okay, and we're going to divide that with 255. Let's just save that into X train. Similarly, we are going to get that for Y. So X test dot as type float 32 divided by 255, and let's just save that to X test. Okay, so we have got the training and testing set configured. Let's run this cell. We got the MNIST dataset downloaded and reshaped properly. Okay, so we are done with two steps. First, we are done with importing all the stuff. Second, we are done with generating the MNIST test MNIST dataset and taking it into training and testing sets. Now we will be taking some network parameters. Okay, third section which we will be doing is defining the network parameters. So in order to define the network parameters, we are going to have a shape. So let's call it as the input shape is going to be the original dimensions which are available. Okay, so that is going to be our input shape. So whatever is the original dimension, so we have got 28 cross 28 equal to 784. So that will be taken here, 28 cross 28 equal to 784. So we have already taken that original dimension at the top by multiplying that. So we have got 784 here in the input shape value. Along with that, we are going to define an intermediate dimensions. So since we are going to perform dimensionality reduction, so let's just call it as intermediate dimensions. So this is going to be the latent dimension, 512 bytes. So we will be learning 512 features. Along with that, we used to take the batch size information for 128. So let's just define the batch size as well, 128. Then we do need to have latent dimensions. Okay. So as I have told you previously in this, there was an article which I have given you, right? Where is that? Here. So here in this article, let's just open it. We have to define the latent dimensions. So I would like to tell you how we will be taking the latent dimensions. Now here. So if you see the images at the bottom of this article, the image of the face and the image of the MNIST. So what we will be doing in here, for the latent features, we will be taking 2 dimensions of our latency matrix. Okay. So this will be dimension 1, that is along the y-axis, and second will be dimension 2, that is along the x-axis. So we will be taking latent variables as 2 dimensions. Okay. So for that, let's just quickly get back to the code. So I'm going to define a latent dimension, and let's say that's going to be 2. Then we are going to define some number of iterations, and let's say it's going to be 50 number of iterations. Okay. So guys, we are done with defining the network parameters. Now what next? So we are done with 3 steps. These are the regular steps which we have to generally do with all the autoencoders: importing, reading the data set, network parameters. Now what next we will be doing? So once we are done with defining the network parameters, now we have to create a variational autoencoder model. We're going to create a variational autoencoder model. Okay. So to create a variational autoencoder model, this is going to be a combination of encoder plus decoder. As I've already told you that we can we can create the variations using the decoder networks, but it was intractable, it was uncontrollable. So in order to make it controllable, we have to calculate the lower bound, and in order to calculate the lower bound, we need to introduce an encoder in the network, and this encoder will be capable of reading the mean value of the features and taking the divergence and standard deviation values, and then it will be generating the sample latent variable. So this sample latent variable will be a controlled sample latent variable, and once you have received the significance of P of Z with X, then you can controllably generate variational images. Okay. So what next we are going to do? So let's build it. So first of all, let's build the encoder model. So in order to build the encoder model, we're going to define the input layer. So in order to define the input layer, first of all, we have to take the shape. So shape is already 700, 784, 28 plus 28, which we have to take. And we have already defined that in the input shape above. So we are going to get that, and we are going to define a name value for it. It's not required. We have not been using it in the previous sessions, but there is a way that you can define the name of the encoder input, because once we will be running our model, if we have to see the summary or the logs of running this neural network, then we can identify the logs of encoder layer, the encoder's input, as well as the decoder inputs. Okay. So just for the log information, I'm just defining a name here so that we can, once we will be running our model, we will be able to identify the logs of each layer appropriately. Okay. So let's just quickly save that into inputs. So we have got an input shape. We have created an input layer. This layer is not a fully connected layer at the moment. So in order to create a fully connected layer, we make use of dense. So let's just make a fully connected layer. In order to create a fully connected layer, we are going to define the intermediate dimension, that is 512, along with the activation. So this activation value will be rectified linear units, and you all are already aware that why we take rectified linear units. Okay. So using this inputs, we are going to generate a dense network of encoder, and using that, we are going to generate, let's say, we are going to generate some features X. Okay. Now, using this X, what we will be doing, so what we have done, we have got input images X. Using that input images, we have created a network, and we have created the X. Okay. So this is something P of X, P of Z using X, we have to generate. So we have got x, and now we have to calculate the mean value, and we have to calculate the log variance, the covariance. Okay, so how can we do that? So let's say we are going to have two more layers here. Okay, यहाँ पे दो layers अब हमें और generate करनी है. कौन कौन सी layers? नेटवर्क डायग्राम में अगर मैं आपको दिखाऊं, तो अभी हमने क्या जनरेट कर लिया, हमने एक ये नेटवर्क जनरेट कर लिया है. ठीक है, इसके साथ में हमने 512 का एक आउटपुट हमने जनरेट कर लिया है. ठीक है, उसके बाद में अब हमें ये जनरेट करना है. वी हैव टू जनरेट दिस लेयर जहाँ पे हमारे पास मीन होगा और लॉग वेरिएंस होगा. ओके, सो लेट अस जस्ट जनरेट दिस. So in order to generate this, what we are going to do, let us just create a fully connected dense layer. And this fully connected dense layer, what it is going to have, it is going to have the latent dimension. Latent dimension is 2, which we have already defined. And let's just call this as z mean. So we are going to get the mean for our latent variable z using x. Okay, so using x, we are going to generate the mean for the latent variable z, and let's just quickly save that into z mean. Similarly, we have to create the log variance. In order to create the log variance, we are going to define the latent dimension, and using the latent dimension, we are going to define z log variance. Okay, using the values of x. So using the value of x, we will be actually calculating z log variance. ओके, तो अब आपके पास जो मॉडल बन गया है, उस मॉडल में हमारे पास हमने अपना एनकोडर बना लिया है. एनकोडर बनाने के लिए हमने अपना इनपुट लेयर बनाया. उसके बाद में हमने एक डेंस लेयर बनाई एक्स की 512 फीचर्स की. उससे हमने एक जेड मीन कैलकुलेट किया, एक लॉग वेरिएंस कैलकुलेट किया. ठीक है, अब ये करने के बाद हमें क्या करना है, अब हमें करना है रीपैरामीटराइजेशन टेक्निक का हमें यूज करना है. ओके, सो रीपैरामीटराइजेशन टेक्निक क्या बोलती है? रीपैरामीटराइजेशन टेक्निक ये बताती है कि आपके नेटवर्क में बैक प्रोपगेशन होना जरूरी है. ठीक है, इन ऑर्डर टू परफॉर्म दिस बैक प्रोपगेशन, वी हैव टू जनरेट द लेटेंट वेरिएबल z, but this latent variable z should be a deterministic variable. Okay, deterministic node होना चाहिए. तो deterministic कैलकुलेट करने के लिए हमें क्या क्या चाहिए होगा? वो कैलकुलेट करने के लिए हमें हमारे मीन चाहिए, हमें हमारा लॉग वेरिएंस चाहिए. उसके थ्रू हम अपना, और जो हमारे इनपुट सैम्पल्स हैं z के सैम्पल्स जो जनरेट हुए, उसके थ्रू हम अपना डिटर्मिनिस्टिक नोड z कैलकुलेट कर पाएंगे. ठीक है, बट उसके लिए हमें पहले सैम्पल्स बनाने पड़ेंगे कि डिपेंडिंग ऑन द इनपुट फैक्टर्स, डिपेंडिंग ऑन द मीन, डिपेंडिंग ऑन द लॉग वेरिएंस, जो हमारा गॉसियन रैंडम डिस्ट्रीब्यूशन है. ठीक है, वो रैंडम गॉसियन डिस्ट्रीब्यूशन पहले हमें जनरेट करना पड़ेगा. सो इन ऑर्डर टू डू दैट, वी हैव टू डिफाइन अ फंक्शन, लेट्स से, एंड वी आर गोइंग टू कॉल दिस फंक्शन एज द सैम्पलिंग मेथड. सो पहले एक मेथड बनाते हैं हम, एक सैम्पलिंग मेथड हम यहाँ पे बना रहे हैं. ठीक है, सैम्पलिंग मेथड क्या होगा? सैम्पलिंग मेथड में हम अपने आर्ग्यूमेंट्स रिसीव करेंगे. वी आर गोइंग टू रिसीव द आर्ग्यूमेंट्स अंडर दिस सैम्पलिंग मेथड. सैम्पलिंग मेथड क्या है? हम अपना सैम्पल जनरेट कर रहे हैं. ठीक है, सैम्पल कैसे जनरेट हो रहा है? अलॉन्ग विद द गॉसियन डिस्ट्रीब्यूशन. ओके, so we will be using the values of mean and log variance, and using that we will be generating our sample. So for that we are defining a function sampling. In order to do this, how we are going to get, so arguments जो यहाँ पे हमने define किए हैं, इस arguments में हमें दो information मिलेंगी. हमें मिलेगा mean value और log variance. जब हम real time पे इसको run करेंगे, नीचे function define करेंगे, तो हम sampling जब call करेंगे, उस sampling में हम दो information इसको define करेंगे. पहली information होगी हमारी mean, दूसरी information होगा हमारा log variance. ओके, सो चलिए डिफाइन करते हैं. तो सबसे पहले हमारा मीन वैल्यू हम रिसीव करेंगे, और हम अपनी लॉग वेरिएंस हम रिसीव करेंगे, और ये कहाँ से मिलेंगे? हमें आर्ग्यूमेंट्स में से मिलेंगे. ओके, तो दिस इज अ वे ऑफ राइटिंग प्रोडक्शन लेवल कोड. जब आप मशीन लर्निंग मॉडल्स बनाते हैं, उसकी प्रोडक्शन लेवल एनालिसिस करते हैं, उसके लिए हम इस तरीके से डिफाइन करते हैं कि क्या सैम्पल्स आएंगे, क्या मीन वैल्यू आएगी, क्या वेरिएंस आएगा, वो हम आर्ग्यूमेंट्स में एज अ लिस्ट मतलब एज अ ऑब्जेक्ट पास करेंगे, एक लिस्ट पास करेंगे, उस लिस्ट के अंदर दोनों वैल्यूज होंगी, उन दोनों वैल्यूज को रीड करेंगे, पहली वैल्यू मीन में, दूसरी वैल्यू लॉग वेरिएबल्स में. Okay, now sorry, so we are going to get the arguments now. So we are using the keras backend. So इसमें हमें shape define करना है. So what k dot shape does, it returns the symbolic shape of a tensor or a variable. ठीक है. So x is going to be a tensor or a variable, and it is going to return a symbolic shape. Okay. So that means you're going to get the neurons of that shape. Okay. So हमने z values की neurons हम generate कर रहे हैं क्योंकि हमें इनका product करना होगा आगे. Z mean will be acting as your bias and log variance will be acting as your weight matrix. So आपके पास x की information होगी, x matrix होगी, उसके साथ में आपके पास Z mean और आपके पास Z log variance की matrix होगी. दोनों का जब आप product लेंगे उसके basis के ऊपर आपके पास samples latent variables generate होंगे. Okay. So for that we are taking it in that way. So let's say we are going to simply call it as batch. कितने batches हमें यहाँ पे बनाने हैं. So depending on the mean we are going to have the batch or bias, you can define it both ways. Okay. Similarly अब हमें दूसरा करना है कि mean का हम dimensions निकालेंगे, कितने number of columns हैं, ठीक है, और उसको हम save करेंगे अपने dimensions के अंदर. So depending on this, we are going to get the number of rows and the number of columns. So you can also call it as rows for easy understanding. कि हमारे पास कितनी rows हैं जो हमारे पास matrix बनी है Z mean की, और कितने हमारे पास dimensions हैं, और हम इसे columns भी कहते हैं. ठीक है. तो rows को generally कहा जाता है, जब हम machine learning terms में use करते हैं तो batch बोलते हैं, कितने set of batch inputs हैं, और जो columns होती हैं उनको हम generally बोलते हैं dimensions. तो आप relevant terms ही use कर लें तो आपके लिए ज़्यादा अच्छा है. ठीक है. That will be easy for you to write code in such a way that other machine learning engineers are also able to understand what you are writing. So now we will be using k. We are going to define the integer shape. So out of that, we are going to extract the value of Z mean and the number of columns out of it. So once we have got the columns, so now we have to have the normal randomization with a mean value of 0 and standard deviation of 1. Okay. So that we are going to calculate. So for that, let's just quickly calculate with k dot random. Okay, we are going to perform a random normalization. So this random normalization, we are going to pass the value of the shape, the batch and dimensions, and with that, we are going to get the randomized values with mean value as 0 and standard deviation as 1. Okay, so this is a randomization technique. This returns a tensor with normal distribution of values. Okay, so we are generating the normalization. So let's just define the shape, that what is the size matrix of the normalization we need. We need the batch and the dimension. So for that number of rows and columns, we will be generating the random normal distribution, and we can actually call it as an epsilon. Okay. So epsilon is the symbol which we have been using in this in your equations, which we have described in the previous article on the previous tab. So that's why I've used the epsilon here. Now, once we're done with that, we will be ready with returning the samples. So just return the samples by defining the mean and just taking the exponential value of 0.5 into Z along with log variance. Okay, and have a product with the epsilon. So what is this? This is actually your samples which will be generated. So how these samples are being generated, I have already shown you the equation using this. So we are going to have that with Z mean plus standard deviation into the samples. Okay, and how we have got these samples? We have normalized the tensors for a specific batch size. Okay, so we have got the batch size as we have taken the batch value, then we have the number of dimensions, we have defined the dimensions. So we got that samples, and using that number of dimensions with our log variance, here they have used the variable Z standard deviation. We are actually using Z log variance. So once we have taken this product, then we have added with the mean and we have got the sample Z value. Okay. Now, so you have got the samples at this stage. You will be ready with the samples, but these samples should be ready with reparameterization technique also. Okay. So as you already know that reparameterization technique is important so that you will be able to back propagate the network. Okay. And here it is defined here that your Z should be a deterministic node, and once it becomes a deterministic node, we will be able to perform back propagation, and then we will be able to learn more partial derivatives of the information available. So now, in order to do that, let us just simply implement the reparameterization trick. Okay. So in order to implement the reparameterization trick, we are going to quickly take the function lambda. For this, we have to specify the function. So the function which we will be taking will be the sampling function, which first we are going to define our sampling function along with the arguments. Okay. So we will be passing the values of Z mean and Z log variance. So we have to pass a list in the sampling function here. Okay. So you can define your sampling function. Now, after that sampling function, you have to define the output shape. Okay. So within this output shape, you're going to make use of latent dimensions. Once we have taken the latent dimensions, next we are going to define this value as the Z value. Okay. So this will become your latent variable along with your, we are going to pass the arguments value Z mean, as well as we have to pass another value Z log variance. Okay. So once we are done with passing, we are going to get the sample generated. So this is going to be our this sample which we have been talking about here. Okay. So we calculated the mean log variance, we calculated the Gaussian distribution, and finally we have calculated the Z. So this is Z which I have already defined to you. What exactly is Z? This is the Z which we will be calculating here after reparameterization. So once we have reached here, now we will be using a decoder network in order to predict the variations of the images. Okay. So I hope this is clear to all of you till here. Now let's quickly go back to variational autoencoder. So, okay, one thing I have to do, let us just quickly save it to Z. I just forgot to save it to Z. So we have got our function defined. Now what we are going to do? So let's just initialize the model, initialize the encoder model. Okay. So yeah, there is a question. Yes, below you can please ask. Initialize the encoder model. If you have any question, you can quickly post a question on chat and I'll quickly take your, I'll let you know the answer by the time. Let us all just continue. Initialize the encoder model. So you can quickly initialize or instantiate your encoder model here. So for that, we are going to create the model. So in order to create the model, we are going to pass in the inputs, which are available. Okay. Along with the inputs, we have to define the mean and the variance which we have taken, Z mean and Z log variance. Okay. Along with, we're going to take the sample Z. Okay. So once we have got this sample Z, we are going to get our encoder model ready. So this becomes our encoder, and I'm going to save that into an encoder model. And once we will be running this, we are going to quickly see the summary of the model so that you will see all the features, that how many layers it has and what is the mean value of it, what is the log variance value, and what is the sample which is generated. All that information will be displayed to you. Okay. So we are going to make use of encoder summary. Along with that, we will be plotting the model also. So in order to plot this model, we need to define another function. Okay. So यहाँ पे हमें एक मॉडल प्लॉट करना है ये बनाने के बाद. तो कैसे हम मॉडल्स प्लॉट करते हैं वो उसके बारे में भी मैं बताऊंगा. ठीक है. So let me just quickly okay, let me just take the questions first and then we'll continue from here. Here, latent dimensions is not defined in, is that how it is supposed to be? Is not defined in line 4. Line 4, we have got the latent dimension on both line 4 and 5. Yes, we have to define it here, the latent dimensions, because we have to generate dimensions on two formats, x and y. That means the x-axis and y-axis for the mean as well as for the log variance, so that once we move towards the x-axis, there will be variations of values in the x, as well as once we will be moving towards the y-axis, there should be variations towards the y-axis also. So here, both the latent dimensions have to be defined. If I have got a question right, and if you understand, that's fine. Otherwise, you can quickly reframe your question. Okay, so by the time you reframe the question, let's just quickly proceed to the question. Yeah, the value of latent dimension has been defined here. We have defined it 2 here. I've already told you that how to define that. I have shown you this article archive where I have told you that there will be 2 dimensions, one along the x-axis and another along the y-axis. So there will be 2 dimensions, and we are using that latent dimension too. Okay, fine. Okay, so yes, we got the latent variables defined. Now let's see. So once we have initialized the encoder model, once we will be working towards the encoding, we would like to plot the model. So I'll come to that point a little later. Plot the model, we're going to define it here. Plot the model. Along with it, before that, let's just go for instantiating our decoder model now. Okay, so for decoder model, let's create. Okay, here we are going to create a decoder model. So in order to create a decoder model, what we are going to do? Decoder model is pretty simple. You need to get the Z samples. Okay, so for that, let's just create an input. Sorry. Let's create the input. We're going to have a shape. For the shape, we are going to have the latent dimension. Okay. Now, apart from the latent dimension, let's name it as Z underscore sampling. We have defined it as Z sampling here. Then we're going to, let's just save it as latent inputs. These are going to be the inputs which will be taken by our decoder model. Okay. Now, once we're done with that, we're going to create a fully connected dense layer. We're going to make a fully connected dense layer with the intermediate dimensions. Along with, there will be an activation function. The activation function will be rectified linear units. Okay. And we have to pass the latent inputs. Latent underscore inputs, INPUTS inputs. Okay. So once we have taken the latent inputs, we are going to save that into X. And finally, we are going to generate the output layer with the sigmoid. Okay. So let's create a dense network with the original dimensions. So we are going to get 784 dimensions received here with an activation function of sigmoid. And we're going to pass in the value of X. So we got that, and let's just save that into outputs. So we are going to grab the decoder model here. So once we are done with generation of the decoder model, let us just instantiate the decoder model also. Okay, let's just call initialize the decoder model. To initialize the decoder model, we're going to make use of model. Let's just take the latent inputs. Okay, we're going to take the latent inputs. We're going to take the outputs which we have generated in the previous outputs, followed by we're going to define the name of this as a decoder. So once we are done with decoding, let's just save that into a decoder model. So we will be representing the summary of the decoder model, how it looks like, and finally we are going to plot the decoder also. Plot the decoder model. Okay, and here we are going to plot the encoder model. Plot the encoder model and plot the decoder model. So plot, I'll come back to this point. Okay. So once we are done with that, finally we are going to instantiate the autoencoder. Initialize the variational autoencoder. Okay. So we are going to initialize the variational autoencoder. So the variational autoencoder will be the decoder model, which will make use of the encoder model along with the inputs provided with the with specific dimensions, and we are going to grab that output. Okay, so we got that decoder here, and similarly, once we have defined the decoder, we're going to generate a model, and this model will be your inputs model along with the outputs. Okay, and let's just define a name for this. Let's call it as variational autoencoder. Okay, and I'm going to save that into the VAE, variational autoencoder model. So that's how your autoencoder model will be created. So we got the encoder here. पहले हमने एक encoder बना लिया, ठीक है? हमने अपनी reparameterization trick यूज कर लिया, इनिशियलाइज कर लिया हमने encoder, decoder बना लिया, इनिशियलाइज कर लिया decoder, दोनों को जोड़ के हमने अपना वेरिएशनल ऑटो एनकोडर बना लिया। अब आपको एक और चीज़ चाहिए, हमें अपने प्लॉट यहाँ पे क्रिएट करने पड़ेंगे फॉर द एन नंबर ऑफ graphs which we will be designing, which we will be tuning in. So I would recommend to perform that plotting thing tomorrow, because we have to create various scatter plots, and we have to create various plots for the input shapes which we will be taking in. So I'll be taking that part tomorrow in the session, because we only are left with 10 minutes and it will take some more time. So let's do that. Let's continue the plotting part tomorrow. Okay. So till now, you guys are done with creation. You guys are done with creation of variational autoencoder models. Okay. So let's just run the cell and save the cells, and later part we will be creating tomorrow. So if I run that here, you can see that I've got an encoder with some number of layers. So I've got an encoder input with 784 dimensions. You can forget about the graph disconnected, the TensorFlow Z sampling. We'll be coming to that. Okay. So इसको अभी हम देखेंगे वेरिएशनल ऑटो एनकोडर फाइनली कैसे हम इसको यूज करेंगे, ठीक है? बट अभी आप सिर्फ ये देख लीजिए कि आपके एनकोडर और नॉन डिकोडर बन चुके हैं, जिसमें सबसे पहली लेयर हमारी 784 लेयर्स की है। फिर हमने एक डेंस लेयर बनाई है 512 की, जिसमें हमने एनकोडर इनपुट्स लिए हैं। उसके बाद में हमने जेड मीन लिया है, जेड लॉग वेरिएंस लिया है। ओके, और फाइनली हमारे पास एक जेड सैंपल जनरेट हुआ है। सो ये जेड सैंपल हमारे पास एनकोडर मॉडल का सैंपल है। फॉलोड बाय हमने एक डिकोडर मॉडल बनाया जो कि उस जेड सैंपल को रीड करेगा। उसमें से पहले 512 लेयर्स बनाएगा, जिसमें 15,036 पैरामीटर्स होंगे, और फाइनली हमारे पास एक डेंस लेयर बनेगी। 784 न्यूरॉन्स उसमें होंगे, जो कि हमारे लिए 402192 पैरामीटर्स जनरेट करेगा। ओके, सो वंस वी आर डन विद दैट, टोटल नंबर ऑफ पैरामीटर्स जो जनरेट होंगे ये हमारे ट्रेनेबल पैरामीटर्स होंगे, और बाकी इसके आगे हम कल कंटिन्यू करेंगे। Okay, so we will be continuing from here. Is that clear to all of you? Please confirm me on chat if you all are clear till here. So tomorrow we will be continuing with defining the plots here. Okay, so let me just quickly write that. We are going to define the plot results function here, where we will be taking a few things like models, we'll be taking data, we'll be taking the batch size information. Let's say the batch size will be 128, as well as we're going to generate the model, and we're going to generate it as VAE MNIST model. Okay, so we're going to define these functions for plot results, and we'll continue that from tomorrow. Okay, so for now you can save your autoencoders and decoders, and let's continue tomorrow on this. Thank you so much everyone for watching.